Hello everyone, my name is Edward Ong, Senior Product Marketing Manager at Power Integrations. First, I want to say thank you for taking the time to listen to this presentation on high-performance diodes for electric vehicle applications. Let's start by first understanding the device structure behind the QSpeed product family of high-performance diodes that enables it to perform much better than traditional silicon diodes. Let's start by first looking at the popular structure for voltage ratings of 300 volt and up. This is what we refer to as the PIN diode structure, and is composed of a P and N junction that enables high blocking voltage, allowing low leakage current. However, this structure tends to switch a bit slower and can have significant amount of switching losses. For diode voltage ratings of 200 volt and below, the popular structure is what we refer to as the Schottky diode structure. So instead of having a P-type material, it's been replaced by a metal layer that interfaces with the semiconductor N layer. This structure has the advantage of fast switching. However, the blocking voltage can be quite low. As such, it can have significant amount of leakage current, particularly at high ambient temperature condition. Next is a cross-section representation of the QSpeed diode. As we could see here that the device structure of the QSpeed has the metal layer Schottky barrier contact that interfaces with the semiconductor N material, and at the same time, it has also deeply buried P-well materials that forms the PIN device structure. As such, this QSpeed offers the combined Schottky and PIN device structure, is able to leverage the advantage of high blocking voltage of a PIN and the fast switching of a Schottky diode. As such, it enables it to achieve low switching losses. In addition, the QSpeed diode is manufactured using a high yield process of 0.35 micron technology and tends to become much smaller than Schottky diodes and hence contributes to fewer amount of capacitance, contributing to a much better efficiency by reducing switching losses. The fab, assembly site, and test sites of the QSpeed diodes are all certified to IATF 16949, which is the Quality Management System for Automotive. Next, we're going to go through the specific product offering for automotive. First off, we'll start with the 600 volt rated QH12TZ600Q, which has rating of 12 amp forward current. This diode is popularly used in onboard chargers, particularly in both the power factor correction stage as the boost diode and in the DC to DC converter stage as the output rectifier diode. This has very low ultra reverse recovery charge of just 9 nanocoulomb at 25 degrees C, and much lower than the silicon carbide diode, which enables it to achieve high efficiency even at high switching frequency, and as such enables a smaller or reduced volume design, a much lighter onboard charger, which are key design criteria for systems in electric vehicle applications. Next one is the 200 volt 10 amp and 20 amp QSpeed diodes. These are match dual diodes that are co-packaged in the surface mount D-pack, and this one is very popularly used for automotive audio amplifier application such as Class D amplifiers and as output rectifier diodes in power supply for audio amplifiers and auxiliary power supplies. When used as an output rectifier diode, due to its soft switching during reverse recovery mode, and is able to eliminate lossy snubbers and hence enables it to achieve higher efficiency. When compared to a Schottky diode, it will have a much smaller physical size and hence a significantly smaller reverse recovery charge, achieving lower switching loss and hence higher efficiency. Let's now look specifically to the power factor correction application circuit for onboard chargers using the 600-volt QH12TZ600Q. So let's first understand how this boost PFC circuit works and the corresponding current waveforms of the switch current, which is the MOSFET, and the current flowing through the diode. So when the MOSFET is turned on, the diode will change from forward bias to reverse bias. And if we look at the current waveform, the blue one represents the current flowing through the diode. We could see a significant amount of reverse recovery current flowing through the diode as it transitions from forward to reverse bias mode. Now, this current, which is a spike current, a significant amount of current, adds to the switch current as the MOSFET is turned on. And it's interesting to note that as this huge amount of current starts to flow to the switch current, that is also the same time when the MOSFET is transitioning from high voltage to a low voltage. As such, there is a significant overlap of voltage and current and hence a significant amount of power dissipation on the PFC MOSFET, causing its thermals to go up significantly. Now, to be able to address this is with the use of the low reverse recovery charge fast switching QSpeed diode. So even as you change the switching frequency to higher operations, the QSpeed enables a significant reduction in this reverse recovery current and allows a significant reduction in the power dissipation on the PFC MOSFET, causing it to operate cooler and at the same time improves the system efficiency for the onboard charger. Let's now look at the QSpeed diode reverse recovery characteristics and compare this with popular fast recovery diodes. So as you could see here on this graph, we have the diode transitioning from forward mode to reverse bias mode. And as you could see here, the blue curve represented by the QSpeed, QH12, has significantly smaller reverse recovery current and a significantly shorter reverse recovery time. And as such, the area enclosed by the current over time represents the charge, which is what we refer to as the QRR. And this significantly smaller amount of reverse recovery current reduces significantly the amount of switching loss, which tends to go higher in proportion to the switching frequency. And this then results in a much better efficiency and a better performance for the system. What you can notice also is that for the tandem diode, it tends to transition in what we refer to as a snappy transition, wherein the current is being turned off quickly and it then generates what we refer to as ringing. And this ringing current, if not properly managed, can then generate a significant amount of electromagnetic noise when we do the compliance testing. And so we could notice here that there's a high amount of DIDT happening in this transition for the tandem diode, which then generates more electrical noise. And same thing with the ultrafast diode. You could see that the ultrafast diode has a significant amount of reverse recovery and hence loss, and soft switching of the QSpeed diode with a gradual transition of the current allows it to not only reduce EMI but also reduce amount of the peak reverse voltage stress that occurs as the diode turns into reverse bias. Now let's look at comparing the QSpeed not just to the popular ultrafast diode but also against a silicon carbide Schottky diode. we could see on the green and the blue curve here representing the QSpeed diodes. At room temperature, junction temperature of 25 degrees C, the reverse recovery charge is somewhere in the 9 nanocoulomb, and that applies even for the 12 amp version of the QH12. As temperature increased, we would expect, particularly for a silicon material, that the reverse recovery charge increases. However, it only increases at a very gradual rate as compared to an ultrafast diode. As such, if you operate the diode at, say, at a junction temperature of somewhere in the 100 degrees C, for example, it will still be significantly lower than a silicon carbide Schottky diode and much lower as compared to an ultrafast diode, which means that you could attain the lowest switching losses and the highest efficiency using the QSpeed diodes, particularly when you operate it at high switching frequencies, which is relevant for electric vehicle designs. In practical applications of onboard chargers, we're talking of 1.8, 3.5 kilowatt modules. What you will find are typically what we refer to as multi-channel, either an interleave power factor correction as shown here on the left side, and this interleave continuous conduction mode PFC would benefit a lot from the use of the QH12 TZ600Q, allowing the power factor correction circuit to operate at high switching frequency, which then enables a much smaller physically design for the onboard charger and lighter as well, which are very critical for systems in such an application. The QH12 TZ600Q can also be used, as shown here on the right diagram, in bridgeless power factor correction circuit. Just to summarize, the QH12 TZ600Q is ideal for onboard charger application either in the power factor correction stage and in the DC to DC converter stage. At worst case condition of 125 degrees C, the reverse recovery charge is still quite small at 30 nanocoulomb, worst case. It has a soft, gentle switching that then reduces electromagnetic interference, both radiated and conducted. It is AEC Q101 qualified, and all the fab, assembly, and test sites are IATF 16949 certified for automotive. Likewise, for audio amplifier and output rectifier applications for aux power supplies, we have the QSpeed 200 volt, 10 amp, and 20 amp dual diodes available and would allow, again, a very high efficiency performance for your systems. For more details on QSpeed product family of high performance diodes, please visit the Power Integrations website, power.com.